I'm here to talk about things from sort of the other end, from the Nashorn guys, who are dealing with fairly small code bases at any one time and trying to get them to run as fast as possible. We're dealing with large code bases, and they've got to run as fast as an old VM, but that'll do. So, I'm Duncan MacGregor. I work as a lead software developer for General Electric in Cambridge in the UK. I'm aardvark179 on Twitter, and you can often find me swearing loudly about this sort of thing, or posting drunkenly on Twitter, but much like Marcus, really. And I work on this Magik on Java project. The reason we've got an alchemist as our sort of symbol for this project on all the slides and stuff is this project was originally codenamed Alchemy because it was one better than Magik. It was moving on slightly, and it was getting gold from lead. So what is Magik? Well, it's a dynamic, weakly typed language. It does absolutely everything wrong in terms of what will get it to run quickly. It's got numeric type promotion that you don't get to have any say in. It's got closures over mutable variables and all that sort of thing. But it's not, and it's got sort of lots of aspects of Lisp and Smalltalk in a similar way to Ruby. But it's not that special as a language. What does make it special is that we're running really large applications. And it's linked to a very particular data store that we use in all of those applications. It's a long transaction data store. It's version managed, so it's a lot like a standard sort of source code management system. You can branch, you can merge, you can do all that sort of thing. And it's optimized for storing geographical data, which is what all our applications are dealing with. And the applications are, as I said, large. How large? Well, small application, or fairly average-sized application that we're running quite often, has 200,000 method definitions in it. And about 10% of those in that particular case are cooked up on the fly when you open the database. They're field accessors, join followers, all sorts of things like that. It gets worse, though. There's other data models out there that have over 4,000 tables in them, so you can imagine the number of field accessors they've probably got in the region of 40,000 getters, 40,000 setters, something like that, of that order. And a lot of customers are running a lot of additional code on top of the applications that we supply. And that 200,000 methods is an average-sized application. We've got estimates that if people try to combine some of our data models and applications, then you're easily in the range of about 500,000 method definitions. Our main concerns with all of this are performance has to be good enough. It doesn't have to be spectacular, but it shouldn't be worse than the old VM, and any extra performance we can get is great. We need to start up and open the database as quickly as we can, which is obviously a problem with the amount of bytecode we've got and that sort of thing. We must not use ever-increasing amounts of memory as we run the application, and warm-up needs to be as short a period as possible, because engineers come in the morning, they start these large design applications. The first impression they get should not be that it's horribly, horribly slow. So I'm going to talk about 3 areas of this work we've been doing today: memory usage, startup time, and the transition from the old VM to the new one, and making that as smooth as possible for our development teams. So I'm going to start with memory usage, and where we started when we first tried Java 8 with this stuff. Well, startup speed relative to Java 7, not good. Not good at all. Memory relative to Java 7, also really, really not good. So took a bunch of heap dumps at various stages of starting the application and looked at where stuff was being used and started making estimates of where we would be if we loaded the full application that we had to deploy. And that really didn't make us look happy at all. That was a moment of almost panic and a bunch of hurried prototyping. So what was using all that memory? Lambda forms, more Lambda forms, and more Lambda forms. Oh, yeah. Concurrent collections, using an awful lot of memory for various things. I'll talk about that in a minute. Atomics that we have to use in various places, using a bunch of memory. And then we get down to everything else. And everything else is comparatively small, so got dealt with a little later. Lambda forms. A lot of the idiomatic ways to use Lambda forms that feel great when you're writing them were terrible as far as memory usage was concerned. Binding followed by adaption, horrible. Drop arguments that you didn't even know was happening in some cases, but was internally, likewise, dear God, no. And these two of adaption after binding and drop arguments made switch points and guard with tests, which you're going to use everywhere in your implementation, depressingly heavyweight and wasteful of resources. Concurrent collections. We hadn't actually expected that one to come so high in the memory usage, but yeah, we wanted a runtime that did not have locks in as much as we possibly could manage. One bad application developer should not be able to lock up a core bit of a runtime and block everything. That's very important to us. So we were using a bunch of concurrent collections and things like that on individual functions to store a cache of adapters and in a few other places. They're great in small numbers, but if you have 200,000 of them, one for every single method and that sort of thing, they really are wasteful of memory. So we had to move away from those. Atomics, again, used in a bunch of places on method tables and methods and functions. This was, again, something that we did for lock-free stuff, but if you've got 3 atomics all held on one object, that's 48 bytes per object that you really would rather not be wasting. And it's even more if you're not using compressed oops. Everything else is the stuff that doesn't scale with the number of methods. Things like Antlers. If you have a parser written in Antler and you let it generate the lexer, that lexer can be gigantic in terms of the arrays it initializes. 40 megs of short arrays is not sensible for a lexer. The amount of time you spend in it, it's not worth optimizing it for speed like that. So you're better off writing your own lexer, but then on the other hand, that 40 megs is constant. It doesn't get bigger with your application, so it's one of the later things you deal with. Things like globals, we're storing them in a prefix tree that is nice and lock-free, but it's not a particularly compact representation, so we need to shift that. Reflection caches, because you want to store a bit of information in the generated bytecode to describe semantics of a method that aren't representable by Java straight. And so you end up looking up methods, and you fill up reflection caches, and they take up a lot of space. Best turning them off. And there's a lot of other small things. They start to go down in size, but there's quite a few of them, so it's worth going through and just optimizing them all as much as you can to reduce the memory footprint. So what did we do on reducing this? Well, we made some prototype branches to do this work in. We wanted to prove that it would work quickly, and we didn't want to deal with all the corner cases. immediately. We changed the MethodHandle adaption order. We cached unbound adapters for CallSites and stuff like that everywhere we possibly could. To get around some of the guard with test problems, we reduced our polymorphic inline cache to be effectively monomorphic and then let things go to megamorphic just as an experiment until there were JDK patches to improve the situation. And we wrote our own version of SwitchPoint because that was one of our biggest problems. So we had sort of CallSite fallbacks that were very sort of traditional. You had a fallback, you bind it to the CallSite, you do some type adaption, and we do a fold to an exact invoker because the fallback returns the method it's just found. That we did originally because in the early Java 7 stuff, doing an invoke from Java was slow and tended to expose class def not found errors that used to bubble up. So that's why we had that original pattern, but it's quite a good one for general stuff. But because you've got that bind to CallSite, things start going horribly wrong in terms of memory. So we reordered all of this. We have a fallback, we do some type adaption, we have an exact invoker, it drops the CallSite argument, we combine those together with a fold, and then we bind that to the actual CallSite, and the fold is now something that we can cache and reuse all over the place. That's very useful. Similarly, with guard with test, we have class checking for our guard with test chains. You're binding the checker to the class that you're checking for, and you're combining it with guard with test. Internally, that puts some drop arguments that you may not be aware of, which don't work well with caching. So we do the drop arguments ourselves to make sure the types are correct. We cache that. Actually, it turns out that you're checking on a subset of the classes quite a lot with the same type, so it's worth caching that using a class value so that it all can get garbage collected away if the class has disappeared. All makes things a lot better. Switch points were inefficient for us because of the use of an immutable CallSite and a dynamic invoker. The dynamic invoker had the same sort of pattern that we had for CallSites. It's got a get target for the CallSite, it binds it to the CallSite, there's then some type adaption, a fold, and an exact invoker. This gets combined by that invoker, but it's not usefully cacheable. It then has some drop argument stuff going on in a guard with test for when you actually want to use that switch point. And that all becomes very uncacheable. So we wrote our own version of SwitchPoint. It does the dynamic invoker in a different order so that is cacheable. And that reduces the resource overhead of SwitchPoint significantly and got us down a long way on our memory usage. Did it help? Yes, it more than halved the number of Lambda forms that were being seen in the application, and that was very good. The application felt faster when you started up because there was a lot more sharing of underlying Lambda forms going on, so things got optimized more. Memory usage was also significantly reduced. This pales into insignificance compared to some of Vladimir's current patch list, which reduced this significantly more. The number of Lambda forms absolutely plummets. They haven't been reviewed yet, as far as I've seen, have they, Marcus? No. No. Yeah. So we're interested in those. They seem to work well for our application. We'll have to track whether they're getting into the JVM in the near future or whether there's going to be some problems with that. Okay. Putting this into production, started tackling all the easy parts, removing concurrent collections, replacing atomics with unset. That gets us a reasonable distance. We're refactoring the CallSites to make them more suitable for this caching strategy and binding order that we're doing. And this work's still ongoing at the moment because there's corner cases that you have to deal with which are a bit awkward in the language. Part of that refactoring of CallSites is going through all the common cases. Method dispatch is a bit complicated in that it's got whether you're dispatching on yourself, whether you're dispatching on superclass, and how many results you're wanting, one, many, or you're just going to pass them on to the caller, so you don't particularly care. All our CallSites supported instrumentation, and that was adding a significant cost to each CallSite in terms of storage, so we want to refactor that out, so it's something that a cost that only needs to be paid if you start with appropriate flags to say that you want that. And all of this adds complexity. So we've refactored our CallSites into a large number of classes, and we're moving towards some more functional composition for all the parts that need to be pulled in at runtime. We can't quite, we thought about using the Java 8 sort of interface default implementations, but obviously that's a little hard to do with stuff that depends heavily on runtime properties. But this sort of functional composition model is allowing us to share a lot of code in useful ways and make it all quite readable. And we've decomposed all the stuff to do with dealing with megamorphic CallSites into separate parts so that is a cost that only needs to be paid by the small number of CallSites that actually go megamorphic. One of the unexpected advantages of this is it's very easy in a heap dump to see what sort of CallSites you've got. So you can see we've got single result CallSites, vastly outnumber every other type. Even though it looks like when you're reading the source code that multiple results are going to be a common case because of some of the places they're used. But single is clearly the one we should be optimizing for, and that sort of thing is going to feed into later development and restructuring of the compiler and that sort of thing in the long term. So startup speed and database opening. Bootstrapping the system, we have a lot of code that needs to be pulled in, and we don't compile it every time. We compile it to bytecode, and so we're really interested in how quickly we can pull that bytecode in. Loading classes looks up MethodHandle constants a lot. That's a fairly time-consuming process. Especially because our production system is running inside an OSGI environment, so we don't work well with the caching that the JDK has at the moment for MethodHandle constants. And loading our languages of module-style packages involves looking up resources for things like messages, and at the moment, because of the way the old VM was implemented, all that stuff is stored in multiple files on disk, and ends up doing a lot of scanning of directories looking for resources and things, and that's slow. So we'd like to look at ways of improving this. Improving the JDK's MethodHandle constant caching. I've got a very rough patch that I've tried and I've shown to Vladimir, and I probably want to discuss with John about security implications of and things like that. But that improves our loading times by 10%. That's 10% of our time was just spent looking up constants. We can probably do more savings by combining the small classes we have to emit from our compiler, because we have to compile, evaluate, and and evaluate small chunks before we can compile the next one. If we do that during compilation, but emit one larger class file, that significantly reduces the number of times you've got to look up constants, and it's probably going to be very helpful. Restructuring our resources is going to be a valuable thing for us to do because that's going to reduce all the number of file lookups and things like that. And we may look at some more radical solutions in that area. Okay, opening the database. An awful lot of metaprogramming goes on with this sort of thing. When you open a database, you look at the data dictionary, you generate a record class for every table, you generate field accessors, join followers, all sorts of stuff like this. And the old VM, coming from a Lispish sort of world originally, that allowed you to save an image after all of this had been done. Once you'd saved that image, you opened it again, it noticed that the database had been opened before, it didn't reevaluate all of this stuff, it just reconnected to the database and verified that it was the same data dictionary that was being looked at. We can't do that. So we had to look at where all the time was going on creating classes and creating methods. Creating new classes required reflection. And the reflection caches were using up memory, so we'd switch them off. You've got to be very precise about which bits you do want to keep reflection caches for, and you've got to do it yourself. You've got to be very careful about what reflection calls you're making. Trying to find a method implementation on an ancestor that doesn't have that method is a very costly operation. So cache that sort of stuff and rewrite anything that foolishly checks for, the 1% of cases where it might hit a problem. If you can avoid that's great. And the other thing we discovered was it really helped to be laser focused in how many call sites you ever invalidate through changing the object hierarchy or changing methods in that hierarchy. We paid a huge cost every time we were going around the loop of defining field accessors because it ended up invalidating a whole bunch of call sites repeatedly every time it went around that loop. And the effects were quite noticeable. So the left-hand graph is before we did any of that optimization work. On the far left, we have our old VM, Magik SF, and we have some Java 7, which was not too bad when you were invalidating call sites, and Java 8, which was horrible. After we'd done that optimization, Magik SF, same speed, different scales on the graph, sorry for that. Java 7, a lot faster, and Java 8 was only a little bit slower, so that was looking a lot better. And this was a test of creating that sort of worst case I mentioned earlier of 4,000 separate tables with an estimate of 10 field accessors per case. So that looked a lot better. But still, not fast enough because you're still having to access the database. So we moved to serialization for this stuff rather than looking at the database every time. We'll just check, we'll serialize in blobs for each data set. We'll then look and see if the data dictionary is actually the same as the stuff we've read in, and this will hopefully be a bit faster. So we need to turn the whole data dictionary into a bunch of blobs, and some of this becomes insanely annoying because there's sorted collections and things like that where a lambda has been passed in as the sorting function. So we have to write a bunch of special cases to deal with the things that are hard to serialize out. We also would like to restore as many of these database connections in parallel as possible. And this is a real trial by fire for your call sites. Ours were thread safe, but it turned out you could get one thread that never got to actually install its target because the other threads were continuously trampling over that call site and resetting the target for things. Eventually, it went round enough times of trying to do this that it managed to, adding one stack frame every time, that it managed to cause a stack overflow. So thread safety in your call sites that will survive any common occurrence, this sort of thing, will exercise hideously. And there's a bunch of additional work you've got to do after you've restored the views because you need to tie them all back together into something that the application will then be able to recognize and work with. So, how much faster is it? Well, reading from the database, restoring a large database took over 60 seconds. Reading from serialization with a single thread, we're down to 23 seconds, I think it is. We will be doing multiple threads for this sort of thing just as soon as we've got the additional work done. And the other thing we've got to do is keep throwing this at larger and larger data sets and more complicated things to find all the special cases of serialization that we might have missed. So that's sort of ongoing stuff as well. The final sort of part of this is dealing with the transition from the old VM to the new one and what developers have come to expect. And there's quite a lot of areas to this, and we're sort of tackling them as and when we can do it. But the first two that we've been looking at is things like code coverage, which people are used to having reported from builds to know whether tests have run and hit particular areas. And developers are not used to the amount of concurrency that we're giving them. I know Charlie has this problem as well, that you're properly concurrent and C Ruby is green threads. We've got the same thing. And lots of applications depend on the limited amount of thread switching that went on in old implementations. Coverage of non-Java languages was surprisingly not bad. We tried Jacoco, which is a code coverage library, and it could instrument stuff without a problem, even for OSGI cases with the right sort of runes given to it. And it could be used on very large test suites, and it didn't break things horribly, so it works quite well. However, reporting the results of code coverage is a somewhat different story. And this is a common thing among a lot of JVM tools. The underlying parts seem to work, but the actual reporting with non-Java languages is less than ideal. Things like Jacoco report coverage by packages and then down at the class level. Well, if you've got a really large code base, that's just not going to cut it because you've got a very large list of packages and a very large list of classes once you've drilled down from that. So you need to start presenting the data in a more hierarchical fashion. The packages need to be in a sensible hierarchy, otherwise this isn't going to help at all. And I don't know about anybody else's bytecode generation, but ours just had arbitrary package names that were guaranteed to be unique but had no real structure to them. And classes in our language had to be compiled to multiple Java classes just because of evaluation order necessity. So it's very hard to track from that report to what's actually being covered in useful bits of instrumentation. And although our class files contained all the source code information that Jacoco theoretically needed to produce a proper coverage map for a file, it turns out that Jacoco and a bunch of other tools completely ignore that information in class files and just want you to give a source file directory which they expect to have the source files in Java, in a standard layout, and otherwise they won't find them. Jacoco is just an example in this case. Everything seems to suffer from this sort of problem to some extent. Changing this sort of stuff is not that hard. It took a whole afternoon of prototyping to get hierarchical stuff and get the source files to be found. Hasn't been turned into proper patches yet, just because we'd like to get another team inside the building to be doing that work, because we want them to be doing more with JVM tools, because that's the direction we're heading in, and it hasn't been their top priority yet. And the changes we need to make to our compiler to produce sensible class and package names are still on the stack of things to be done. Threading was another area where we reckoned developers would need a significant amount of help. So we wrote some prototypes of instrumentation tooling that would tell you where threads have been spun off and would tell you all the stuff to do with passing values via atomic queues and things between threads, and and which threads were claiming locks and that sort of thing. And this is very useful, but it turns out in almost all cases, if people have written code that does stuff with atomic queues or does locking, then they've thought about the threading issues and there's no problems. All the bad cases are where people wrote code without any thought of threading at all, just setting global variables or slots or whatever on instances all over the place, and until we put in some really fine-grained instrumentation for global variable access and slot access on individual objects, we're probably not going to be able to help them in tracking that stuff down. It is an area of worry. We found some bits of application code with absolutely no thread safety in their design that worked through pure accident up until this point. They had no right to work on the old VM. They really didn't work on the JVM, and we're just having to help them deal with those problems as we come across them. Hopefully, there's not too many, and hopefully we can write some better instrumentation tools for them. But again, this is something that has to be worked on, and it'll be good to have that as something that's pulled into the CallSites as needed based on runtime variables. So, to summarize, MethodHandle caching and reuse is absolutely vital if you're going to get any of this stuff to scale above moderate test cases. If you're running large applications, it almost doesn't matter if it doesn't perform as well with shared use of method handles and things like that. It's the only way you're going to get the memory to a sensible level. Serialization and optimizing metaprogramming really, really help with startup speeds. And we're going to keep having to look at that area, whatever happens, because we want to get those down as much as possible. And there's no easy answers for fixing any of the concurrency issues that I've found. I don't know if Charlie has. Nope. Yeah, it just comes down to working with individual application teams and helping them dig down into what might be going on. So that's our sort of little adventure in getting this stuff to scale. And if anyone's got a question, just shout it out.
You talked about your versions of some of the lambda forms method handles, like the switch point one. Do you call through that in the chain? I mean, is that one piece of code that's generated and then it will pass through and bind on the other side? The reason I'm asking is one of the big advantages we have just using the built-in method handles is that, in theory, it's all going to inline and specialize through for whatever call site it is.
Yeah.
But if you're generating a piece of code that sits in the middle of that, you're breaking that process, right? Technically, we may be breaking that process, but honestly, we can't pay the specialization cost. They were just too large. So the cost of having, like, basically your own utility switch point
It's
less than
it is less in terms of memory. The problem you hit with a lot of regard with test stuff is we were looking at how much retained heap each call site was using, and it was getting up to the order of a whole K of retained heap when you had a couple of, when you had a sort of polymorphic inline cache of more than one. Obviously, if you've got 200,000 methods with all the, even if you're not hitting all of them, that sort of memory usage just starts to get too high as the application continues to be used. So we're prepared to pay in performance terms if we have to, just to get that memory down.
Okay. And one quick comment on your call site validation. In JRuby, our call sites, they are picks. We are about 6 wide, I think, was what the failover point for it was, when it was actually cheaper to just do an inline cache. But we all have a...
Yeah, sure. So we have a 6-wide pick. It's configurable or whatever. But then we also have a second count that's just the number of times a call site's been invalidated for any reason, which is like 1,000 or 10,000 or something. So that helps us avoid, in the long term, call sites that never settle. Eventually, they just fall back to the dumbest possible inline cache, and then we don't have the invalidation cost after that.
Yeah, that's an area we've been looking at. Actually, on the startup side of things, we've sort of gone the other way of, we keep a count of how many times the call site has been touched at all, and we only bother to install targets if that actually gets high enough. A large chunk of startup time was spent just going through the fallback, installing the target, returning that fallback, returning that target, it being executed. And in Bootstrap code, that was often a call site that was never touched again, or was only touched 1 or 2 times. And that turned out to be a big win just because of the cost of installing targets.
I would say the interpreter that we have helps avoid a lot of that, because we can be stupid for a while and then be smarter later.
Yeah, and in that area, we probably would be better if we'd done an interpreter, but we'd gone for a very sort of pure, just go for a bytecode compilation immediately. And we'd have to have built a big framework to store the bytecode compilation we had done, because God knows you don't want to compile 200,000 methods every time. Anyone else?